Mechanisms in motion are short revision videos which show you the effect of arrows in organic chemistry mechanisms. As the format is a quiz, you will be presented with multiple options for how the mechanisms will occur. Based on your choice, move ahead to the timestamp and you will see how your choice affects the reaction. If you are correct, you will move on to the next step in the mechanism. If you choose the incorrect or less likely answer, the reason for this will be explained and then you'll be given the correct answer. Friedel-Crafts acylation is a type of EAS, or electrophilic aromatic substitution reaction. EAS reactions allow for the functionalization of aromatic compounds like benzene. The reaction conditions for Friedel-Crafts acylation are an acyl chloride, a Lewis acid like aluminum trichloride, and an aromatic compound. The first step in Friedel-Crafts acylation is the activation of the acid chloride with the Lewis acid. This either occurs by activation of the oxygen at the carbonyl or by the activation at the chlorine. Activation at the oxygen would occur by the oxygen lone pair attacking the aluminum of the aluminum trichloride. This would result in a negative charge on the aluminum and a positive charge on the oxygen. While coordination could occur here, this does not result in an electrophile electrophilic enough to undergo Friedel-Crafts acylation. Activation at the chlorine would occur by the lone pairs from the oxygen pushing down to form a triple bond, allowing the carbon-chlorine bond to break and attack the aluminum trichloride. This results in an acylium ion which has a positive charge at the oxygen of the carbonyl. Due to the distributions of electrons between the oxygen-carbon bond, this molecule is very likely to undergo electrophilic attack, as this would restore the carbonyl double bond and quench the positive charge of the oxygen. This is the correct step. The acylium ion seen here has another resonance structure. To form the other resonance structure, you can break one of the carbon-oxygen triple bonds, pushing the electrons up to the oxygen to quench the positive charge. To reform the original resonance structure, the arrows are reversed. This means that a lone pair from the oxygen is pushed down to reform the carbon-oxygen triple bond, leaving a positive charge on the oxygen. The next step in Friedel-Crafts acylation is the attack on the electrophile. However, there are two different resonance structures that can be drawn for the acylium ion. Which resonance structure is the dominant form and therefore should be the structure you should be attacking? Having a positive charge on the oxygen may seem less stable than option A. However, all atoms in option B have a full octet. This means that option B is more stable. If you look at option A, the carbon of the carbonyl does not fulfill the octet rule, which makes this molecule less stable than option B. The next step in the reaction is the attack of the benzene ring on the acylium ion. There are three different positions on the benzene ring which can be substituted: position A, B, and C, corresponding to the ortho, meta, and para positions respectively. Which position will preferentially attack the electrophile? Attack from position B would have to occur by directly breaking the double bond of the anisole. While this reaction could occur, the presence of the methoxy group on the ring makes this option less likely. Attack at positions A and C are both possible in this scenario. The methoxy group on the ring is an electron donating group. This means that the lone pair of the oxygen can push electrons into the ring. In doing this, you can either break the first bond or the second bond from the methoxy group. If you break the first bond, you will form the product A by attacking the acylium ion. In this position, the product formed is called the ortho product. If you don't attack using the first bond, you can push that bond over one position in the ring and use the next double bond to attack the acylium ion. This would result in the product forming at position C, or the para product. Both of these products are more likely to occur than the attack at position B, making both A and C possible products. However, the ratio of the products will vary depending on the reaction conditions and can be hard to predict. In this video, we show the attack at the para position. To attack the electrophile, the double bond of the benzene ring will break, attacking the carbon of the carbon-oxygen triple bond. This will cause one of the carbon-oxygen triple bonds to break up to the oxygen, quenching the positive charge. After the electrophilic attack, there is a positive charge on the benzene ring. In order to restore aromaticity, the benzene ring needs to be deprotonated. Deprotonation can either occur at position A or position B. Deprotonation at position A would cause the double bond to form. However, the carbon next to the ester would now have 5 bonds connected to it. This is called a pentavalent carbon and is never allowed in chemistry. Therefore, the only option available is position B. Deprotonation at position B reforms the double bond. This restores aromaticity while not forming a pentavalent carbon. This is the correct option. This slide shows the overall reaction scheme for Friedel-Crafts acylation. This slide shows the reaction mechanism with the curly arrows drawn out as you would draw it in an exam. Thanks for watching the video. If you found it helpful, please leave us a like or a comment, and subscribe if you'd like to see future videos of mechanisms in motion.